Okay, so this is a start to Unit 12, which is the second to last unit of this very weird school year. This unit is all about the distance, the length of like chords, secants, tangents, and arcs. Last unit we looked at angles and circles. We dealt with the measure in degrees. This is going to deal with distance, so the length. Today we're going to look at specifically chords. And if you have two intersecting chords, if we want to find the length of the chords, well, there's like kind of a rule, I guess, and I'll get into why this works. But it's going to be A times B equals C times D, or in other words, when two chords intersect, then the product of the partition segments of one chord equals the product of the partition segments of the other chord. I like to think about it as the piece of one chord times the piece of the other. So A times B equals the piece times the piece. So A times B equals C times D. Okay, we'll look at a pretty basic example, and then we'll go into the proof as to why this does work. So filling in some things, they tell us that we have two chords, A, B, and C, D. AE is 6, BE is 4, DE is 3. What is the length of CE? Okay, so piece of one chord times piece of the other. 6 times 4 equals piece of one chord times piece of the other. 3 times x. So we're looking at 24 equals 3x. Divide by 3, and x equals 6. So if we're kind of looking at it notation-wise, it's going to be AE times BE is going to equal DE times CE. Okay? So the reason why this does work has to do with similarity. So taking a look at here, we have two intersecting chords. I'll just go ahead and highlight the ones we're specifically looking at. So AB and DC intersect. So since AB and DC intersect, then we could say, based on kind of the rule that I just taught you, we could say that AE times BE is equal to DE times CE. And the reason why that is, like I said, has to do with similarity. So the reason why ACE and DBE are similar is because, okay, for one, we have vertical angles. And then the other reason, the other angle we can get would be angle C and angle B are congruent. We know that they are congruent because they are both inscribed angles from last unit, and they intercept the same arc. They both intercept arc AD. So if angle C and angle B are both inscribed angles and they intercept the same arc, well then they have to be congruent. And then the same thing works for why angle A and why angle D are congruent. Again, they're inscribed angles and they intercept the same arc. Now, that these triangles are similar by angle-angle, since these triangles are similar by angle-angle, we can say that if triangles are similar by angle-angle, then their corresponding sides are in proportion. So I can set up a proportion. I could say side CE is going to correspond to side BE. I know that because I have one hash mark, two hash marks, one hash mark, two hash marks. I could also say that AE would correspond with DE. Again, 3 hash marks, 1 hash mark, 3 hash marks, 1 hash mark. We could also say that AC and DB are correspond, but we're not going to worry about those because we don't need them. Since the triangles are similar, corresponding sides are in proportion. I could set a proportion. I could say CE over BE is going to be equal to, if I started with this triangle, then I'm going to go ahead and do AE over DE. And the reason for that would be corresponding sides of similar triangles are in proportion. Now that if we know sides are in proportion, well then we can cross multiply. And if we cross multiply, we get AE times BE is equal to DE times CE, which is our rule. That's our rule that I wrote up here right from the beginning. So that's your proof as to why this does work. Now that we know this proof and we know that rule, let's just go ahead and answer some pretty basic questions. So this would be 10 times 6, piece times piece equals piece times piece. So we get 60 equals 5x, x equals 12. 12 is going to keep those, make that work. Okay, moving on here, a little bit different. They say AB bisects chord CD. Think about what a bisector does back from very early in the year. A bisector splits something into two congruent segments. So if CE is x, then DE also has to be x. Okay, let's use our rule. 8 times 9 equals x times x. 72 equals x squared. It says simplest radical form. So we're going to square root both sides. If you square root, that gets rid of the square. Let's break this down. So we have to think about the largest perfect square that goes into 72. Our perfect squares, I'll write them on the side real quick. Kind of goes on forever here. The largest perfect square that goes into 72 is 36. The square root of 36 is 6. So in simplest radical form, it is 6 radical 2. And then this last one, again, just slightly different. It's going to require us to do a skill we learned from Algebra 1. 2 intersecting chords, okay, fine. So we'll go ahead and do 3 times 4 equals x times x minus 4. Okay, let's distribute out the right side. Now we have a quadratic. We have an x squared. So we're going to move everything over to one side and set it equal to 0. We need to factor. We need to ask ourselves what two factors multiply to negative 12 but add to negative 4. So we have to multiply to negative 12, add to negative 4. That's going to be negative 6 and a positive 2. Negative 6 times 2 is negative 12. Negative 6 plus 2 is negative 4. So this factors to be x minus 6, x plus 2, set it equal to 0. Tee this off. X minus 6 equals 0, so x could be 6, or x could be negative 2. We have to ask ourselves, do both of these work? Do one of these work? Do either of them work? And our only answer here is 6. We have to substitute back in. If I substitute back in, I get 2 and I get 6. That works. If I substitute negative 2 in, I'm going to get negative 6 and negative 2. That doesn't make sense because lengths need to be positive. So our answer would just be 6. Okay. Looking a little bit more at chords, so here's a property. In a circle, a radius or diameter perpendicular to a chord. So if a radius or a diameter, so in this case we have a radius, if a radius is perpendicular to the chord, then it also has to bisect that chord. So that must mean that AE and BE are going to be equal. They're going to be congruent. So if a radius is perpendicular to a chord, well then it has to bisect that chord. And we'll go ahead and use that property to answer some of these questions here. So we could see that we have in this circle, this radius is 5, CE is 2, fine. What is the length of BD? And they're telling us that AC is perpendicular to BD. Okay, let's think about a few things here. All right, first off, we have a couple of radii. O to D is a radius, so O to B is also a radius. So if this is 5, well then this one's also going to be 5. We'll see what that does for us. Might do something, might not. Notice OA is also a radius, and OC is a radius. We know part of this radius is 2, which means this other part has to be 3. Okay, we want to find the length of the entire thing BD. Well, let's think about this separately. We have a right triangle going on here. We have that this is a right triangle, and it's actually a right triangle on the other side as well. Think about what we can do for right triangles. If we're missing one of the sides, so I'll call this x. If we're missing one of the sides, we can go ahead and use the Pythagorean theorem. So if I went ahead and did that, I would get x squared equals 16. So x would have to be 4. So d to e is 4. But remember, if this is a diameter and it's perpendicular to a chord, then it bisects the chord. So b to e also has to be 4, which makes the length of BD equal to 8. Take a look at another one of those, because these are a little bit tricky. Okay, they tell us all of this AB is 8, but I see a radius, and I see a chord, and I see a perpendicular line, which means that it must bisect it. So if this whole thing is 8, well then we could break it apart and say 4 and 4. We want to know the length of just this, O to P. Okay. O to C, this entire thing is 5. What we have to do with this question, and what makes it a little bit tricky, is we have to draw in our own auxiliary line. So auxiliary line, if you remember a couple of units back, that is your own line that you're drawing in. I just drew in a radius. I drew in radius OB. All radii are congruent. All radii are equal. So if radius OC is 5, then radius OB also has to be 5. Okay, now we have something that we can work with. We have a right triangle, and I'm missing one of the sides. If I have a right triangle and I'm missing one of the sides, once again, we can go ahead and use the Pythagorean theorem. So I could do a squared plus b squared equals c squared. So that's 16 plus x squared equals 25. This actually is a Pythagorean triple, just like the last one. It's a 3, 4, 5 right triangle. So O to P has to be 3. Okay. In this one, they're telling us D to A is 2x plus 2. B to A is 4x minus 6. OC is a radius. DB is a chord, and it's perpendicular. Well, if it's perpendicular, then these are congruent. So we could say 2x plus 2 equals 4x minus 6, and solve it out. So we're going to get 8 equals 2x, and x equals 4. I'm going to skip this this next one. Don't worry about it. Okay, and last thing here. If we have chords that are parallel, they intersect congruent arcs. So if AB and CD are parallel, then AC and BD have to be congruent. So that's a pretty straightforward one here. Looking at this first one, if AE is parallel to BD, then which statement must also be true? Okay, if those are parallel, then arc DE and arc AB are going to be congruent. So let's see if we can figure that, if that's one of them. Yep, choice 3. DE and AB are congruent. And the last one, we have the fact that AB is parallel to DC. So if AB and DC are parallel, well, if arc AD is 60, then arc BC is also 60. We want to find out the measure of angle CDB. So we want to find out this inscribed angle. That's bringing back last unit. An inscribed angle is half of the intercepted arc. So it's 30 degrees. All right, so we'll stop there. We'll take a look at some more segments the next lesson. All right, have a good day. Bye.